Hello and welcome. In this second half of 8.3, we're going to look at finding the center of mass of objects in 2D. But before we get there, let's look at the center of mass in one dimension. So figure 3 shows a picture of the x-axis, which is our one dimension, and we have three masses represented by these three dots. So they're like, you can imagine them as being objects just laid out on the x-axis at these x values. So the masses of the objects are M1, M2, and M3, and the locations along the x-axis are X1, X2, and X3. The fulcrum is right here at x equals 0 in figure 3. So the fulcrum is going to be, you can imagine this being like one of those teeter-totters where the fulcrum is right in the center. But in this case, the fulcrum is not exactly in the center. And the masses are just people that are sitting on the teeter-totter, right? So we have two people on the right side of the teeter-totter and one person on the left side of the teeter-totter, it looks like. Now, if they're, if the heavier people are sitting on the right and there's some light person on the left, well then the teeter-totter is going to turn in a counterclockwise kind of motion. And that's because of this rotational force called torque. So torque is this turning effect in general of a mass on a rigid body, the rigid body in this case being the x-axis or the teeter-totter that you're sitting on, with a fulcrum. And the fulcrum is what the teeter-totter is sitting on top of that makes it kind of move back and forth like this. So torque is a rotational force. In general, torque is represented with this tau symbol. It's a Greek letter tau. And generally speaking, you get torque by, if you have everything in vector form, which is, we're not going to cover it here, but I just want to mention this in case you see it in physics or in Math 280, you run across this. So we can find the torque by taking the force, often due to gravity, but it could be any force in general, and crossing it with the distance from the object to the fulcrum, which can also be a vector because it's going to be actually a displacement kind of vector. So that's in general how you find the torque, but in our cases of one dimension and two dimension, we're not going to have vectors going on here. So instead what we'll do to calculate the torque is take the force due to gravity of each of these objects and just multiply it by the x values, which are going to be the signed distance away from the fulcrum, at least when the fulcrum is at x equals 0. So for the first mass, we're going to have, the first object, we're going to have M1G, M1G represents the weight of that first object. And we'll take that weight, that force due to gravity, and multiply it by x1, which is, again, that signed distance away from the fulcrum, which is at 0 right now. Then we're going to add to it the torque of the second object. That'll be M2G x2. And then M3G x3 is going to be the torque of the third object. And if we add up all the torques, that'll give us the net torque of the system. Now if the net torque is positive, then that's saying that the whole system is going to be rotating clockwise. If the net torque is negative, the system will be rotating counterclockwise. We can change the torque of the system by moving the fulcrum. So right now the fulcrum is at x equals 0, but that can be changed. You can move the fulcrum over to x equals 3 if you wanted to, and that's going to change the torque of the overall system. One thing is that the torque that we're going to be most interested in finding is where the torque is 0, where everything is perfectly imbalanced. It's like if you have a heavy person on one side of the teeter-totter and a light person on the other side of the teeter-totter, if you're able to move that fulcrum closer to where the heavy person is, then you can, at some point, find a perfect balance between the heavy person and the light person. So what we're going to be looking for is that perfect balance point called the center of mass. You do it whenever you try to balance something. Like if you're trying to balance a pen on your finger, you're not going to hold it over on one closer to the ends. You're going to hold it more in the middle, because that's where the balancing point is going to be. I'm terrible at balancing pens, as you can now see. So the torque is 0 when the fulcrum is placed at the what's called center of mass. Which we're going to label using x bar, so x with a little bar over it. And we're going to ask the question right now, how can we calculate this x value? How can we calculate this x value? Well, suppose we move the fulcrum over to x bar, where we're going to try to find what x bar exactly is. We'll try to find a formula for it, but we'll just call that place where we're going to move that fulcrum x bar. So on the next page in figure 4, it shows that picture. So now the fulcrum is at x bar. It was over there at 0, but now it's over at x bar in figure 4. So what we'll do is try to write the torque of this new system, the net torque. Well, the torque of this new system is going to be the weight of that first mass, so m1g, times the signed distance from the fulcrum. So here the signed distance is going to be x1 minus x bar. Remember that objects that are on the left of the fulcrum are signed negative distance away from the fulcrum, and then objects to the right of the fulcrum are assigned positive distance from the fulcrum. So if we want to keep x1, it's to the left of the fulcrum. If we want to keep that assigned as a negative distance away, we'll take the x value, which is negative to begin with, because it's to the right of 0 and left of 0, and subtract x bar, which is this positive number. So a negative number minus a positive number, that's going to give you the negative signed distance away. So that's the torque for the first object. For the second object, we're going to do the same kind of thing. Write the weight, the force due to gravity. Then we're going to write x2 minus x bar for the same kind of reasons. And then for the third object, it'll be the weight of that object, m3g, and then times x3 minus x bar again. Now if you do x3 minus x bar, you're going to get a positive number, which is what we want. We want a positive distance from the fulcrum here. To get that positive value, you do the right x value minus, which is x sub 3, minus the left x value, which is x bar. So it's actually always the same. It's always going to be whatever x value you are minus the x value of the fulcrum, at least when you're in 1D. Now what we want is we want this torque to be 0. If x bar is supposed to be the center of mass, then this net torque should compute to 0. This is the sum of the torques equal to 0. Sum of the torques equals 0 at the center of mass. What that would say is that there's no net rotation. Everything is perfectly in balance at x bar. Now our goal is going to be to solve for x bar. Notice one thing is that every single term has a g in it, the acceleration due to gravity. Let's get rid of the g to simplify things by dividing the whole equation both sides through by g, and now g will be gone. That kind of makes sense. The balancing point shouldn't depend on the force due to gravity. If you're on Earth or on Mars, the center of mass of this pen, the place where you're going to balance it, should be the same. Whoops, apparently that wasn't it. It should be the same. It doesn't matter what the acceleration due to gravity is. So then we have plus m3 times x3 minus x bar equals 0. Now we can distribute everything out. We'll distribute out the m1, the m2, and the m3. And now we're solving for x bar, so we're going to move all the x bar terms to one side and then factor out the x bar. That's not a very good m. So we'll factor out the x bar and then divide by what we have left. And so we should get x bar equals m1x1 plus m2x2 plus m3x3 over m1 plus m2 plus m3. A short way of writing that, because we only have 3 masses in our system, but we could have any number of masses in our system. So a short way of writing that in general would be the sum of m sub I x sub I over the sum of m sub I, where I would go from 1 to as many masses as you have. So this this would give us a formula then for finding the center of mass. The top part of that formula, the sum of m sub I times x sub I, is sometimes called the moment of the system about the origin. So all it is it's the torque of the system about the origin, but with the acceleration removed, with the g disappeared, gone. So we're going to use the letter capital M to represent the moment, and little m to represent the sum of the masses. So thank you for watching, and in the next part we're going to look at center of mass in 2 dimensions.